Welcome guys. So in the previous video, we already talked about linear vector space, quotient space, linear transformation, kernel, and image, and hum, and yeah, and also direct sum. So most of the ingredient are in the linear algebra is already tell. Okay, so in this video, we talk about the linear independence. And basis. Okay, properties is the most important. Yeah, so definition. So so I say that V, so give a V vector space and over field F. So I say so when I say V is a linear combination of V1, V2 up to Vn, all these V are belongs to the vector space V. Means that my V can be written as alpha 1 V1 plus alpha 2 V2 up to alpha n Vn, which all the alpha I belongs to field F. Okay, so this is called a linear combination. And I can define a span. Okay, so let me just, okay, let me, using origin. Okay, so given a set, so non-empty subset of V, then I can define LS called the span of S, right? Also called span of S. So basically, these are all the vectors in V, such that V is finite linear combination of vectors in S. Right. So basically, you take any finite vector in S, and then you do a linear combination, and collect all of it. This is called span. Okay. So theorem. So it's very easy. The span of S is just is also a linear subspace of V. Okay, so easy to check that the two finite expansion of two finite linear combination S addition will be in, and their addition will be still in LS. So basically, you need to check that if alpha in LS, beta in LS, easy to check that alpha plus beta in LS. Also, check the constant multiplications in S and in LS. Okay. Okay, so quick lemma. So this lemma is also easy. So if S is a subset of T, obviously that the span of T will contains span S, right? So LT contains span LS. Also, and LS union T will be LS plus T, right? Just because union means that you collect all the vectors, right? So this is the same as you addition two vectors, right? Sorry, this is LS plus LT. So this is a direct sum. Okay, so this is all trivial. What you can think, because you take S union T, right? Means that you can take S or E or T, right? So in the direct sum language, you take S as the first component, T as the second component. Okay, also LLS, right? You already spent, right? So you take any finite linear combination, you still get the same thing. So LLS is also LS. Okay, so linear independency. So definition. So when people say that the V1, V2 up to Vn is linear independent, so means that if there exists alpha 1, alpha 2, alpha n in F, such that the alpha I, Vi 0, then you must have all the alpha I 0. So yeah, this is if. So this is the definition. So definition means that if there exists a linear combination of V such as 0, then all the coefficient must be 0. This is called the linear independence. So let me just write down the words, linear independence. Okay. Okay, and otherwise called the linear dependent. linear dependent, or this is linear independence or linear independent. Okay. Okay. So theorem. Right. So if you get you v1 vn in the v, which is a linear independent, then you can take a span of it. Okay. So basically, this is let's call it w. So the theorem says that every vector in w, every vector v in w has unique has unique will be a unique, so will be a unique linear combination of v1 v2 up to vn. Okay, so what I'm saying is that you take any vector v in it, right, and so v can be written as alpha 1 v1 up to alpha n vn. This alpha are unique. Okay. Right, so it's trivial, right? Suppose not. So let's say you find alpha to alpha, alpha to alpha, alpha 1 up to alpha n, and beta 1 beta 2 beta n, such that your v is alpha I vi I from 1 to n, also equal to beta I vi I from 1 to n, right? So you can write this as I from 1 to n, your alpha I minus beta I vi 0, right? But by definition, these vi are linear independent. So since vi are linear independent, so alpha I equals to beta I, so unique. Okay. Okay, so theorem said that if v1, v2 up to vn in v, either so now you given us you pick set of n vectors in v, so there are only two cases, either linear independent or what, some vk is a linear combination. It's linear combination of the preceding ones. Okay. So these preceding ones means that v1, v2 up to vk minus 1. So what I'm saying is that given a set of given you pick n vectors in the vector space v, then either two cases happen. The first case is they are linear dependent. Okay. The second case is that you can find some vk such that vk is a linear combination of the previous k minus 1. Okay. Yeah, so hope you guys hope you understand this by your intuition, right? But I seldom talk about examples because I think this is so examples are somehow trivial. You can check it by yourself. Okay, so right, so if they are linear independent, then of course we don't have the proof. If not, that means that we can find non-zero. We can find some non-zero, not all these zero, such that it is 0, right? So all of this is so not at least one of alpha is non-zero, right? So right, so let k, so I choose k be the largest integer, which alpha k is non-zero, right? So I pick k is largest integer, which alpha k is non-zero, right? So now for I greater than k, then all of the coefficients so for k is the largest integer, which is non-zero, right? So what it means is that for I greater than k, your alpha I is 0, right? So what you get is that alpha 1 v1 plus alpha k vk is 0, and the alpha k is non-zero, right? So you can write vk as 1 over alpha k minus alpha 1 v1 minus alpha k minus 1 vk minus 1, right? So vk is the linear combination of preceding k minus 1. Okay. Yeah, that's so this is has the corollary. Okay, so corollary tell you that so if v1 up to vn in w is a let's say if v1 in v up to vn in v have W as linear span. So basically, you take some W, which is a linear span, and then let's say V1, V2 up to Vk are linear independent. Then we can find a subset. So we can find a subset. We can find a subset of V1 up to Vn of the form. Let's say V1 up to Vk, Vi1 up to Vir. Consisting of all the linear independent elements whose linear span is also W. Okay, so yeah, so I mean I don't want to write, but you guys know what I'm saying. So basically, you take. So basically, you take some vectors, you take n vectors, right? And you take another vector subspace W. And if if you can find if let's say the first V1 up to Vk is a linear independent, then basically you can find you can find a subset of V1. So basically you can try to extend this. Yeah, extends the vectors you get. Such that the linear independent element whose linear span is W. Let's see. So if you okay. So this is, let me just write it word, write the equation. Oh, okay. So what I'm saying is that yeah. So if W is a span of V1 up to Vn, okay. Okay. So it's a subset of V, and the first K are linear independent in V. And theorem tell you that you can find the rest. So you can find, let's say Vi1, Vi2 up to Vir in W, right? Such that you can replace all the rest. So basically, W is span of V1 up to Vk. So which these are linear independent? These are also Vi1, Vir. Okay, and such that all of these are linear independent. So basically, given n vectors, right, you can always you pick some linear independent set, and you can replace the rest of it into a linear independent. So this is the call. Okay, so proof. So if V1 Vn are linear dependent, then we are done, right? Because these are already span W. So if not, right, then we can wipe out, right? We can wipe out. We can wipe out some Vj, which is if the Vj is the linear combination of the previous one, right? Up to that. For example, if Vj is linear combination from V1 to Vj minus 1, then I just cut out Vj. Okay, so I keep cut. Okay. Okay, so I will, if I cut Vj, then I will get some vectors like this. Suppose I cut Vj. Okay, so since Vj is the linear combination previous one, so I cut out, right? Right, and since it is, right, so also span of it is still W, right? Because this guy is Vj is also linear independence, so a linear combination of the previous one, so their span is still W. Right, and I mean, then I can keep going, right? I can keep going. I can keep X, W, J. I keep going and delete. But finally, right? But finally, finally I will get some vectors. Right? I will get some set of vectors. Let's say it's V1 up to V k, right? Up to vk is still fine, right? Because vk is linearly independent, and there are several of them will survive, right? But by our construction, several of them must be linear independent. Okay, because if it's not linear independent, then I just cut out, right? So the rest of them must also span up. Okay, so these are all what we want. Okay, so this is a proof. Okay, so let's call the title. So let's call it dimension. Let's define dimension. So how should I say? Okay, so let's just so if I say V is finite dimensional, so means that there is this V1, V2 up to Vn in V, such that so n is finite, right? So such that span V1 up to Vn is V. Yeah, so basically all the vectors in V is the basic linear combination of some vectors in V. So this is a basic, right? This is just the ideal basis, right? But basis need to be linear independent. Okay. But this is the 5 dimension. Okay. Okay, so the subset of V is called basis. If so if the first span as V, the second is S is a linear independent. Okay, so it's the same. So there's so if V is finite dimensional means that the S is finite. Okay, so you can easily check that these two are equivalent. Okay. Yeah. And then use the previous same theorem, right? If you pick n vectors in V such that span in V, then you can eliminate the linear independent one, and the rest will be linear dependent. Linear independent. So finally, the rest will still be finite because you start from finite and then you cut something, so your final result will be finite. So you can see that these two definitions are the same. Okay. Okay, so there is a small theorem that also intuitive. So we say that V1 up to Vn is a basis of V. So this is the basis, and also W1, W2, Wm in V are linear independent. So in the n-dimensional vector space, by the way, so the number of S is defined to be the dimension of V. Okay, so it's not obviously now obvious for now say that n is actually invariant. So maybe V can have the two bases which the element are not the number of elements are not the same, right? But actually it cannot happen. Yeah, so that's purely theorem. So if Vn is a basis of V, and W2, W1, Wm in V are linear independent, then obviously that from your intuition you can easily prove that M less or equal to N. Okay, so proof is trivial. Why? Because by definition, right, your Wi are linear combination of V, right? Wi are linear combination of V of the V1 up to Vn, right? So W1 is a linear combination of V1 to Vn, W2, right? It's also a linear combination of V1 to Vn. W3 is also a linear combination of V1 to Vn. Okay, so by definition, by definition, right? Yeah, right. This is a definition. Okay, so from here that let's see. So from here we know that let's say we pick Wm and V1, V2, Vn are linear dependent. Linear, right? Are linear dependent. Right, because Wn is a linear combination of V1 and Vn, right? So they are linear dependent. Right, and then they also span V. Right, so there's span V. Right, so the proper subset, so by definition, the proper subset S, right, in this set will span V. Okay, So you can, I mean, okay. Okay. So let's say the proper subset, basically, if you fix WM, and by definition, you can cut out something, right? So you will get VI1, VI2, up to VIK, right? Where K is less than n-1, right? Because your total has, you need to, you already know you must cut one of it, right? But so your rest will be K less or equal to n-1. Okay, so it's a basis of V. Okay, so now yeah, let's trade off, right? So let's trade off this VI1 and then replace it by WM-1, and then we can do the same thing, right? Okay, so now I will get WM-1, WM, VI1, VIK. All these are, so this is also a basis. But remember that W is also a linear combination. So all of this, right, will still span V, right? But you can still possibly cut out something. Okay, and you keep going, right? But finally, you must span V, right? So you will arrive the result that M must less or equal to A. Okay. Okay, so by these results, right? So if V1 is the basis of V, then W1, Wm are linear dependent, and S then M are less or equal to N. Right. So conversely, if you get two bases, right, all of it are linear dependent and span V. So you use this lemma for this, you exchange V and W, right? So you get N less or equal to N, and then greater or equal to N. So you finally prove that if you get the base finite dimensional vector space, then all the bases has the same element. Okay, so the result is that the basis of V is invariant. Okay. Okay, theorem. So this theorem is important. So if you get the field N, so remember that the field parentheses N means the vector space of n dimensional, and each element looks as a tuple of F, right? Isomorphic to Fm if M equals to N. Okay, so if M equals to N, then this direction is trivial, right? So we only need to prove these directions. All right, so let's say Fn has a basis, right? 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, right? Right, so the number of the bases is N, the number of bases M, right? So obviously that if M is not the same as N, it's not. So M must be yeah. So if M must equal, if M is the same as N, then this is trivial. And if they're isomorphic, that means the number of bases is the same, right? So you prove this direction. So M must be equal to. Okay, because the basis of V is invariant. Okay. Okay, so the theorem, this is another. So if V is finite dimensional over F, when V is a vector space, finite dimensional vector space over F, and V is isomorphic to Fn for some. Okay, this is also simple, right? Because V has a basis V1 up to Vn, right? They are linear dependent, so you can construct a linear transformation V up to Fn just from a V1 map to the standard basis 1, 0, 0, 0, 0, V2 map to 0, 1, 0, 0, 0, and Vn map to 0, 0, 1. Okay, so easy to check this is injective. Okay. And things are not independent also on two, right? Because any Fn is basically a linear combination of it, so you can play it back. Okay, so this is isomorphic. Okay. Okay, so yeah, so we get another results. Basically, yeah, it's basically any two. Yeah, I think I don't have to write any two finite dimensional vector space over F of the same dimension are isomorphic. Okay, the reason is that they are all isomorphic to Fn, right? So if you have same dimension, which you are all isomorphic to Fn, so basically you're isomorphic. Okay, so this theorem said that if V is finite dimensional, so if a dimensional V is finite, and W is a subspace of V. Okay, and then the first thing is trivial. The dimension of W is less than infinity. So basically, less or equal dimension V. So means that W is finite dimensional. Also, the second is that the quotient is basically dimension V minus dimension W. Okay, so the first one, let's see how to prove the first one. Okay, so first one, what I'm saying is that dimension V is less than dimension W is less than dimension V. Okay, okay, so what is easy to check that you can pick. So let's say we pick V1 up to Vn is a basis of V, right? By definition, it's also basis of W. Sorry, it's not basis of W, but the least set, right? Any vector, so any vector in W is a linear combination of V1 up to Vn, right? Because W is subset of V, right? So you already know that any vector in W can be written as linear combination from V1 to Vn. So the dimension of W less than dimension of V, because you can try to cut out and pick up all the linear independent one, which is just subset of this, right? So finite set, the subset of finite set is still finite. Okay, so this is part trivial. Okay. Okay, so the dimension, the only difficult the only a little bit maybe not easy to see is this. Okay, so let's see. Right, so I can right you can provide a linear standard onto map from T to V quotient W by map any vector X into X plus W. Right. So let's see, you map all the bases, right? You map V1. Let's see. Okay, so you pick. So now you pick out basis of W. Let's say pick out W1 up Wm, which is a basis of W, and then you and then you find out the rest, right? You put like say V1 up to Vr, which R plus M is N, right? You pick all of it that as a basis of V. Right? So you pick a basis of W, and then you choose another R basis to fulfill all the requirement, which all of this contains become a larger space. Okay, and you ask about what is the least linear map, right? So if for W1 you map to W, right? Because W1 W, so W1 plus W is W, right? And up to Wm, so all this map to W, right? So all of this map trivially into W. Okay. How about this? So let's define V1 bar, so it's basically TV1, and V2 bar is TV2. So up to like VR bar is TVR, right? So this V1 bar is just V1 plus W. This V2 are just V2 plus W. These are VR plus W. Okay. Okay. So let's see. So right, you see any vector V can be written as alpha 1 W1 up to alpha M WM, and also beta 1 V1 up to beta R VR, right? Construction. And then you go into the image, right? You go to the image. So once you go into the image, your TV1 become beta 1 V1 bar, right? Because all of this W cut out, right? So you get beta 1 V1 bar and the beta 2 V2 bar up to beta R VR bar. Okay. Okay, so and you know that this map is onto map, right? So you know that the V quotient W is spanned by V1 bar, V2 bar up to VR bar, right? Okay, so you know that the dimension of it must less or equal to dimension V minus dimension W by definition. Okay. But why is the minus sign? Why is the equal sign now? Okay. Okay, so now I want to prove that they are linear dependent, linear independent. Okay, suppose not. So suppose not. Suppose not. Suppose not means what? Means that you get gamma 1 v1 v1 bar up to gamma r vr bar, which is 0, right? Which tell you that so this is t something, right? But the 0 means what? 0 means what? All of these are what? Are in W, right? So all means that the alpha gamma 1 v1 up to gamma r vr is some vectors which in W. Okay. But W, okay, right? So it means that you can write lambda 1, W1, lambda and WA. Okay. But we say that all of these are linear independent, right? So which tell you that the gamma 1, gamma 2 up to gamma VR must be 0. Right, so all these V1 are linear dependent. Okay, since they are linear independent, they also span V quotient W. So we prove that they are bases, right? So dimension of V quotient W is basically dimension V minus dimension W. Okay, so final theorem, which is just a corollary, I think you can check by yourself. It's basically if you get the ABR subspace of V, and you can ask about A plus B. Okay. So obviously, if the AB are the same vector space, then A plus B will be the same. Okay, so check by yourself that dimension A plus B is dimension A plus dimension B minus dimension A intersection B. Okay, so the proof is let's just quickly sketch. Okay, so if you know the abelian group theory, you know that you get your A quotient A plus B quotient B will isomorphic to A quotient A intersection B. So this is the group isomorphism theorem. Okay. Or you can use a linear algebra, but I mean you can if you view AB as just an abelian group. Okay. And then you take dimension. Okay. See you guys next videos. Hope you guys subscribe to my channel. Thanks.